starting the recording back up again, so we'll have 2 videos for today. Big picture, first off, and then a new system of notation. You get to learn to write hierarchical notation in terms of multi-level models. We have avoided that up to this point, haven't needed it. So, orienting us back towards kinds of longitudinal data and the kinds of models that would make sense to consider for it. Where we just were is the within-person fluctuation side. So like the psoriasis example, some people have worse severity all the time, some weeks are worse than others. So if I were to put in a slope for time, if this were my data, it would have nothing to do. So there's no point. That's why there was no effective time in example 4, because we didn't need one. There was no systematic change. Where we are headed for, as I guessed, about the next 7 weeks or so, is models of change. And here we are going to be focusing on 2 different things that are complementary and simultaneous. With respect to the model for the means, that's where the fixed effects go. Our job is to describe the pattern of change on average. Like, what does the average trajectory look like? Is it linear? Is it nonlinear? Is it continuous or discontinuous? Does it go up and stay up? Does it come back down? All of those sorts of decisions. On the variance side, we are doing 2 things. On the surface, we are seeking to describe individual differences in each of these aspects of change. So do people differ in only their intercepts, or do they also need their own change slopes? If the change slopes are bendy, do they need their own bendiness amount? So how many sources of individual differences are there in describing that average trajectory and the variation around it? That's sort of the substantive goal. But at the same time, under the hood, so to speak, what's happening is that random effects related to time are building in new kinds of covariance patterns. They are time dependent, and they are functions of continuous time rather than discrete time. So these models will work for unbalanced data and unequal interval data, any kind of data you want to throw at them. So they're more flexible in that regard. Sounds cool, huh? Yeah. And by the way, what we're doing is also called growth modeling or growth curve modeling. Even if they're not growing, they're declining, and even if they're declining linearly, that is still a growth curve model. And if you want to sound fancy, what other adjective do you stick in front of it? Starts with an L. Latent, yes. That latent growth curve modeling does not mean growth of a latent variable. It means you did your growth curve modeling in the SEM store as opposed to the MLM store. That's what it means. So models for the means then, as questioned at the beginning of class, up to this point we've only had 2. Empty, nothing in it but a fixed intercept, or saturated means, treating time as discrete, as a categorical predictor, in which we would have 1 fixed intercept and then n-1 slopes in terms of n being the number of occasions. So in the same way that we had compound symmetry as the most parsimonious option and unstructured as the least parsimonious, you can think of these directly as parallel, but it's with respect to describing the means, which is the job of the fixed effects. So our goal is to find something in between. We're trying to play name that trajectory, spend fewer parameters than all possible to reproduce it. And also, if we're creating a trajectory, a continuous function, then we don't have to have balance time. Saturated means is only possible given balance time, because otherwise you would have to estimate a separate mean for every single unique value of time in your data set, and at some point that's going to break. So, like I said, directly parallel. On the other side, we still have this idea of compound symmetry being the most parsimonious model for the variance. That would work for longitudinal data. Unstructured is the answer key. Everything gets to be what it wants. We're shooting for something in the middle. But instead of making it something in the middle like Toeplitz or autoregressive, something in the middle is going to be including random slopes related to time. That is going to build in different patterns of variance and covariance that hopefully get us as close to unstructured as possible while spending fewer parameters. Question from the Zoomers, what is balance time again? Balance time means that everybody is being measured on the same schedule. So if I had like pre-test, post-test, and follow-up, that's balance time. Doesn't matter how far apart in time those are, that is equal interval or not, which is a separate distinction. So unbalanced time would be like someone shows up not at time 1, but like a day later, and then someone else shows up at time 2 a week later, and you keep track of exactly how long it is in between the occasions. So time can be a truly continuous variable in these models. So back to basics. Remember this slide? Okay, it's coming back. So in this process, we're not dealing with R-only models, we're dealing with models that have levels to them. So on the variance side, we have level 2, U0, this thing is a random intercept. Each person theoretically has one, but these are not what we're being estimated. We are estimating the variance across them instead. So tau squared sub U sub 0, to me, is random intercept variance of the U's across people. Conceptually, this number, whatever it's estimated to be, represents all the reasons why people differ in their means over time. And we would need time invariant predictors to explain that. So person things, things that people bring with them that carry with them across time. Then the E's, once we've given each person their own mean by deviating the U from the grand mean, E is what's left. It is the discrepancy between what you have as an outcome in each occasion and what the model thinks you should have had based on your intercept. So these are all the reasons why some occasions are higher than others within persons after controlling for your own usual tendencies. So time-varying predictors would explain E-variance in this case. Welcome to official multi-level model notation. If you were in the clustered multi-level class last time, you're like, hey, this looks familiar. Yep, you're going to see all the same slides with different subscripts. These ones came first, which is why occasionally you'll find a TI in the clustered class that isn't supposed to be there. And in terms of equation notation, I'm back to not putting things in the equation editor because that makes the file so big that it crashes when I try to save it. So this is just regular font. So if you can live with that for the sake of easiness. So this is where we start from. This is an empty model in a general linear models context where y sub I means I only have one outcome per person. Beta 0 would be a fixed intercept that is shared across people. And E sub I is the residual for that person's Y. So if I had one level of data, this would be sufficient. To write this same idea using hierarchical notation, so this is the notation scheme that was, I think, invented by the HLM folks, Radenbush and Breich, in the 1980s or so. They brought this into education and it kind of became their thing to write the models this way. They have swapped out a couple of things. So Y has picked up a subscript. It's per time, I don't know what I was going with that, time and I for individual. So that's level 2 is individual in this case. Because Y has picked up a T, so does E. So E is per time and per individual. So this is stacked data. Now beta 0 I has changed what it means. It has not only picked up an I, but it's not red anymore. And I'm using the colors very deliberately. Red things are to be parameters in the model for the means. Blue things are to be parameters in the model for the variance. Beta 0 is not a parameter. It is not. It is a placeholder. It is a backpack, if you will, in which to stick in the level 2 parameters and carry them down to the level 1 model. So placeholder is the term that I use in the textbook. It is the term that I think is most directly intuitive because it's just a container. That's all it is. So at level 2, beta 0 I is how each person is going to get their own intercept. It is a function of a fixed intercept plus a random intercept. The fixed intercept is the thing in red that looks like a Y. That's a gamma. In this font, it looks more like a Y. So gamma has a 0, 0 because it is the first predictor in level 1 and it will become the first entry in this prediction. So we're going to have double subscripts on all the fixed effects from here on out. I think seeing the pattern will make it easier to follow. And then U0 we've already met. What is that? Yeah, that random intercept. So it has a mean of 0. It is how far off the fixed intercept your random intercept is. So if you put these two together, then you get the whole variable for what the intercept is. The fixed part is in common. The u part is your own specific deviation. And we don't estimate these u0s directly. We instead estimate the variance across persons in them. That's the model parameter. Likewise, we don't estimate the e's directly. We estimate the residual variance at level 1, sigma squared here. And if you're like, this seems unnecessarily complicated, you're not wrong. Here's the composite equation, as it is sometimes called, where you just write the things out. And you can see from this more directly that there's only 3 things in this model. There's a fixed intercept in the model for the means. There is going to be a random intercept variance in the model for the variance, and a level 1 E residual variance as well. And as a side note, to foreshadow the connection to structural equation models, other folks would describe beta 0 as a latent variable. You're like, huh? So in general, the connection is that the fixed effect is the mean of that latent variable, and the random effect variance is the latent variable's variance instead. So beta 0 could also be drawn as a circle in SEM notation, and that is like 50 slides from here, give or take. And if you're like, what? Never mind. Placeholder is sufficient for now. So this is, I've named, empty means random intercept. Colloquially, in like papers, you will see this described as just empty model, or intercept only model, or unconditional model. Like those are the terms that people use. I tried to make this more specific as to what I mean by empty, meaning the fixed effects are empty. We do have something in the variance model besides a residual. Okay. Here is the other one that you know, a saturated means random intercept model. We could do that one. It would look like this. So note I've expanded the level 1 model to have 3 new terms, time 1, time 2, and time 3. Those would be dummy codes that distinguish each of these occasions from a reference occasion of time 0. Note that each of the betas has an I to it. So each of these is in turn a placeholder for how the model will form a slope differentiating time 1 from 0, time 2 from 0, and time 3 from 0. In this model, though, they only contain one fixed effect. This notation, then, I think is a little bit easier to see the pattern. In terms of the subscripts of the gammas, the red things, the first subscript is what beta does it go with in the level 1 equation. So the first one starts with 0, the second one starts with 1, the third one starts with 2, and so on. So which beta at level 1 is the first subscript in these fixed effects? The second subscript in these fixed effects is which term within that beta equation. So they're all starting with 0 here because they're the first thing that defines beta 1 or beta 2 or beta 3. And if I wanted to write it more simply, this is the composite equation that would just substitute in the fixed effects directly because I still only have one random intercept and one residual here. Question?
So in the composite one, for this one, the random intercept variance is like separated from gamma double 0, but in the earlier model, for the empty means, beta 0 was composed of those two things together. Is it okay to separate them, or do we have to keep them together, or do we have to separate them?
So I put them in parentheses to emphasize that this is the beta 0 part. I could have done that here, but because I didn't do that for the others, I just stacked them up in terms of fixed effects and then variance things.
Okay.
For folks who write equations this way, this is what I'm typically used to seeing, is all the fixed effects first and then all the residual type terms at the end. I don't think that's a requirement, but it is a convention.
Okay.
And I think it is just as correct to write it out as level 1 and level 2 as to write it out in composite. It's a discipline specific sort of what are people used to seeing it as. Yeah. Either way, if you have a random intercept only, that's compound symmetry. So you can set that up as an R-only model, or you can set this up as the GNR version. And so this is the same information that you've already had in lecture 4, just reiterated here. So this V matrix, the end result of putting the GNR back together again, can be converted into a correlation version, and then the off diagonals are given as the interclass correlation. So in this case, if the interclass correlation is estimated after controlling for which occasion it is, we would say that's a conditional or adjusted interclass correlation, whereas the empty model version would be unadjusted. The adjusted one will often be a lot smaller. Or bigger, actually, bigger. Make that back. All right, 125. How are we doing? We're hanging in there?
Can you go over that last slide again? Putting in the matrix?
This one or
No,
this?
the matrix one.
This one. Okay,
Yeah,
sure.
Thank you.
Yeah. So this is showing you how the model is predicting what the pattern of variance and covariance would be across occasions. If you only have these two things, like what that translates into looks like this. Random intercept variance lives in G. This part wraps around it so it's the right dimensions to add to R. This is saying that there is no remaining relationship over time after you control for the intercept variance. So mean differences between people is the only reason that these outcomes were correlated in the first place. So if you stick this random intercept variance everywhere in this matrix, you get to this pattern right here, which is V. And so this is a covariance. If I take this divided by that as the denominator, that's my formula for interclass correlation. That's also the formula to convert a covariance back to a correlation more generally, as right here. And so the correlation version of this matrix gives you the interclass correlation.
So basically these models, the empty means model, the saturated means model, like they can be represented differently, or they give us the parameters for the fixed and random effects, and then the G and R models tell us where to house those different components of variance.
So the fixed effects set up predictions for each row of the data set. Like what is your y hat supposed to be? And then what's left over is being structured with this pattern.
Okay.
So conceptually, if everyone is measured, let's just make it the simple case. If everyone's measured at 4 occasions and they're the same 4 occasions, then time does not have any between person variability to it. Everybody's on the same schedule. So putting in these fixed effects related to which time it is should reduce part of the E variation. Because some of this was, well, why are you off your line today? Oh, because it's time 2. Like, and if everybody else is high at time 2, then that will explain some of this variance. But this is the pattern of what's left over. And so this would be the interclass correlation of the leftover patterns of variance and covariance. All right. So how about random slopes? Can we talk about that briefly? Without matrices, I promise. At least for the next 15 minutes. It's Tuesday, right? It's garbage day. I was going to say no more matrices this week, but no, I'm going to lie. They're going to come back on Thursday. But we got pictures. So this is a class about longitudinal analysis. One of the most common questions that people would ask is, what is the pattern of change over time? How do people improve as a function of this treatment? Or how do children's behaviors improve as a function of, what do you call it, Alex? Give me a word. Like when you work with kids in clinic and you try to make them behave better?
Yeah, so like increase like their adaptive or pro-social behaviors.
Sure. Yeah, so is your treatment effective? How would you know, right? These are the questions you would want to ask by following a child over time and seeing how their behaviors change as a function of external and internal things.
Yep.
Yeah, so this is like a bread and butter type question in terms of longitudinal models. So there's 2 parts to this question about change. Number 1 is there an effective time on average? Like on average, is your treatment working? On average, are children growing? Are they increasing in their pro-social behavior, etc.? If so, then that's what fixed effects related to time are for. The more interesting question, though, and the part that ANOVA is not designed to give you, is does that average effective time vary across people? Does each person need their own slope? If so, you need a random effect of time. And in terms of vocabulary, here is how I am using these terms, because they have a lot of different ways they're used in the literature. Fixed means everybody gets the same. If it is a fixed effect, it is a constant. It applies to everybody's score equally. It does not get an I subscript. If it is a random effect, that means everybody gets their own. So random doesn't mean like, oh, that's like so random. It's like, no, it's actually something systematic. There's something systematic about a person that is showing up across all of their occasions, and we believe that that is attributable to them needing their own slope. A random slope allows each person to have their own slope. So if we look at just the simplest case of linear change, I have 4 pictures for you in which the intercept is going to be random in every figure. So we are assuming from the starting point that everybody needs their own intercept as either a baseline or their own mean. You can think of it either way to some extent. So this picture, in which y is going to be my outcome, x is my metric of time, the heavy black line is the average for the sample, and the thin black lines are example trajectories through, you can picture like some points here going around each line. So I have labeled this picture no fixed, no random, because on average, there is no effective time. The line is flat. So if you put in a fixed slope for linear time in your model, your coefficient would be estimated close to 0, likely be non-significant. Now I have no random here because that flat line holds for everybody. It's not that it's flat, it's that it's parallel. That's the key point here. Everybody, no changes, the same. Picture B on the top right is showing what it would look like if there was a positive fixed linear slope for change over time. On average, folks are going up to some extent, but there's still no random slope for time because everybody's changing the same. That one fixed slope works equally well for everybody. And these are the only 2 situations in which univariate repeated measures ANOVA is going to give you the right answers. Because if people all grow at the same rate, if they stay parallel, then the variance stays the same the whole time, and the covariance likely will too. So these are pictures that would support a compound symmetry or random intercept only model. All right, with me so far? Okay, now the more interesting case. No fixed, but yes random. So let's say that you do your dissertation, and because you're a masochist, you decide to collect your own longitudinal data. So you spend 2 years collecting data. You're going to fix something, right? You're going to treat people, you're going to make them better. And you go home after 2 years of data collection. You've got your data, you're so excited to analyze it, and you run your ANOVA, and your omnibus main effective time is non-significant. Wah, wah. So you might cry, you might feel sad, and then you might come talk to somebody like me and be like, is there anything I can do? And I would probably ask you to make a picture like this. And if your picture looks like this, your story just got a lot more interesting. Yeah, on average, there's no fixed effective time, but that's because some people got better and some people got worse. People need their own random slopes. Now, I don't know about you, but if I did a study where I was trying to help people, and some of them got worse, I might want to know who those people are, right? Like, what is it about this person that made them respond negatively as opposed to these people that responded positively? The only thing that can predict that is person-level characteristics. Why do you need a negative slope, but they need a positive slope? It has to be something about you that is constant across time. So you can have one without the other. You can have a non-significant fixed slope, but you would have random variance around it. And in that case, the fixed slope stays. You can think of the fixed slope as the center of the distribution. If you take it out, then you're saying that the center is exactly 0 from what the random effects are going to be deviating around. And that is not a good thing to do. And you can have both. You can have improvement on average, the extent of which varies by who it is and their characteristics. So building through these perspectives requires potentially testing fixed slopes as well as random slope variances. Here's what B would look like. So a model that is consistent with the cell B here, where we've added a fixed slope of time, but we have not yet added a random slope. This is what that model would predict. So level 1, y for each occasion t for each person I is a function of an individual specific intercept placeholder. At level 2, beta 0 I is still built out of two things: fixed intercept, what everybody gets, random intercept deviation, the u0, how far off your intercept is. We have beta 1 has an I, that's also a placeholder, and it's multiplying time as a predictor. So this is a column in your data set that can take on whatever values a person has. Doesn't need to be balanced, doesn't need to be equal interval, can be whatever it is. And that idea is operationalized by giving time a TI subscript. So time could be unique values for every single person. Because of this inclusion of time, the definition of our fixed intercept has to adjust. So it's 136. Let me throw you a softball question. What's an intercept?
Prediction when all the predictors are 0.
Yeah, the expected outcome when all your predictors are 0. So given that time is now a predictor, this fixed intercept is specific to time 0. For that reason, time 0 needs to be somewhere in your data. Now, in my later class, I teach them about centering for this reason, and if they forget to center, like in life, there's no consequence. Like, okay, your fixed intercept is an impossible value because 0 is not within the scale of your predictor. Okay, fine. In these models, this can break stuff. Not this one, but in the one with the random slope. Having a 0 value for time that's outside the scope of the data can break the model. So time 0 is something that you want to think about ahead of time. Time 0 is most often the first occasion, doesn't have to be. So for instance, in my book, in chapters, I'm going to go with 7 and 9, there's an example looking at problem behavior in fictitious adolescents, because I made up the data, so they're not real. And the study runs from like 13 to 18, and because problem behavior for an 18-year-old might have more serious consequences, like putting the intercept there makes more sense than having it at 13. So if you want to figure out, like, predict individual differences and where people end up, putting time 0 at the end of the study would make sense to do that. If you want to predict individual differences in where they start, putting time 0 at the beginning would make more sense for that. It's a choice. Just somewhere within the data is what I would highly recommend. So this fixed intercept is now conditional on time 0 because we've added this fixed slope. And beta 1 right now has only one thing in it, gamma 10. That's going to be my average slope. So just, that's it. This is the rate of change per unit time. And
so
go ahead.
if you end up adding the random effects, then that'll get added into beta 1.
This is where the random slope is going to go. Yep. And more generally, every beta can have a fixed part and a random part that goes into the level 1 equation. Yep. The composite model then uses parentheses to show where the betas would have been. So the first parenthesis here, that's what beta 0I is taking care of. And the second one is beta 1, just this part right here. So because the effective time is truly fixed, everybody gets just this number. Everybody's supposed to change the same according to this model. I knew I wanted to make that point. I just forgot I had done it with animation. Yeah. Okay. Yeah. I think that's enough. Because the next thing is like a new thing. But questions? Yeah, let's do that. Let's answer questions.
Can I ask for the ages 13 to 18 study where time 0 is 18? Are your other times negative?
Yep. Yep, you would center it such that time equals age minus 18. And so the rest of them would all be negative. Yep. Other questions? All right, then let's see. Homework is due tomorrow night. You can be finishing that. Thursday, we're going to keep working on this. I'm really hopeful to have example 5 done by Thursday, but I'm not sure if we'll get to it, so we'll find out. And the schedule for things being due from this point forward is likely to be adjusted at least somewhat. I got to figure out how and by how much, and I'll communicate that via the webpage and via email. All right, so you're not free yet. You have to come back on Thursday. Then after that, you have a whole week off. From me, at least. All right. Zoomers, thanks for being here. Thanks for your patience. Roomers, thanks for being here and for your patience. And let me know if you need help. Bye for now.